Hi everyone. In this video, I'm going to cover the answers to the practice exam here. So we will move through this. I'll explain kind of in detail my thought process for going through each question. All right, question one, part one on spectroscopy. Which of the following statements is true about the molecular ion in a mass spectrum? So the molecular ion, of course, gives us the mass of the compound, and this compound, upon injection into the mass spectrometer, gets bombarded with high energy electrons, and that bombardment will cause the ion to lose an electron, and typically from a lone pair or pi bond first, and then that produces a radical cation. A radical is an unpaired electron, and so sometimes you'll see that written as this, a radical cation, where we have the unpaired electron and then the charge representing the cation part of it. So lost a pair of electrons, no. Gained a pair of electrons, no. Gained one electron, no. Lost one electron, and it does not carry a negative charge. Okay, so understanding the conceptual pieces of the mass spectrum will be helpful for this test. Now we're moving on to question two. Which of the following bonds vibrates at the highest frequency? So frequency is proportional to energy. This is frequency, nu, h is Planck's constant. So the higher energy, energy is proportional to bond strength, at least for atoms with similar masses. And we know that the bond vibrational wave number depends on the mass of the atoms in the bond, and also the bond strength. So, as I just said, the energy for bonds with identical elements will depend exclusively on bond strength. So we have CH, 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 and CH here. So what's going to be the determining factor here? Well, the only real difference between these CH bonds is the hybridization of the carbon bonded to that hydrogen, and the more S character, the more electronegative that carbon is, and the shorter this bond will be, shorter, stronger bond, then would require higher energy to vibrate, higher frequency to vibrate. Frequency is expressed in wave number for an IR, so we'll end up having higher wave numbers for this as well. And that's why the alkyne CH stretch appears at higher wave numbers than alkene or alkane CH stretching. Okay, so hybridization does affect bond strength, as we know from our foundations, and therefore we see that in the IR spectrum. So some more experimental evidence to support that. Question three, we're making true statements here. Shielded or deshielded protons experience a net magnetic field strength that is higher than shielded or deshielded protons, requiring a higher or lower frequency to flip the spin. So we know that as the magnetic field increases, the energy to flip the spins from the alpha and beta state increases. So the difference in energy here will increase with increasing magnetic field B. So keep in mind what's happening here. We're applying a magnetic field. Electrons around those protons shield the proton from the magnetic field. It's like you're standing in front of a fan that's blowing really hard at you. You use your X-Men superpowers to shield yourself from that fan, and now you're feeling less of that. You have shielded yourself. Okay, so deshielded protons experience the magnetic field that is higher than shielded protons. And that effect of deshielding, right, withdrawing electron density, requires higher frequency. Again, that's a higher energy because frequency and energy are proportional to flip the spin. Okay, so you really have to have this concept down to get all the credit here, because there's no partial credit for this. In the electromagnetic spectrum, high or low frequencies large or small wave numbers and short and long wave lengths are associated with high energy. Okay, so energy is proportional to frequency, E equals h nu, and then we can combine C equals lambda nu, this is wavelength, combine these to get E equals hc over lambda. This is Chem 110 stuff. So high energy would be high frequency, and short wavelengths from there. And then how does that relate to wave number? Well, it's large wave numbers because wave number is proportional to energy as well. Okay, so knowing those concepts and relationships in the electromagnetic spectrum will be useful. Keep in mind that IR spectroscopy uses infrared, hence the name IR, and then radio waves are used in NMR. And so NMR is very safe in terms of the energy of that electromagnetic radiation. It's the same concept that's used in MRIs, magnetic resonance imaging. So different tissues have different concentrations of protons, and so by using MRI, this nuclear magnetic resonance technique, we can see differences in those types of tissues. All right, so moving on, question 4. Match the isomers to their corresponding IR spectrum, and then provide the structure in each box, label the diagnostic piece in the IR. All right, so I'm gonna ignore the structures right now. I'm just gonna look at the IR. So for compound 1, we definitely have an OH stretch here. We have some CH stretching for alkanes. Everything else is irrelevant. Then we have the CH alkane stretching, not important. We have a CO double bond stretch here. In the third one, we have this peak here would be the CH stretching of an alkene, and that's important to note. This is probably some impurity, and that's really all we need from these to be able to narrow it down. The only one with an alcohol is the cyclopentylmethanol. The only one with a carbonyl is this guy, and then the only one with an alkene is the ether with the alkene. Okay, so don't get too caught up in looking for things that aren't there. We really are just using this to identify functional groups. You have to be able to recognize the common functional group, stretching frequencies and whatnot. And besides that, I'm not going to ask you to, go too deep here. All right. So you get points for the structures and then points for labeling appropriate bonds in the IR. Question 5. This compound, ethynylbenzene, can be treated with conditions A or B to produce 2 different isomeric carbonyl compounds. This is a ketone, and this is an aldehyde. All right, so provide the conditions A and B that produce each product. So we have our reaction sheet. You can get it out. I need a nice sound effect here. Alkynes, especially terminal alkynes, we can add a group to either side of this triple bond. And to add it to the less substituted side, we're going to add dicyamylborane. And you need the cyamylborane rather than BH3 because these cyamyl groups, which are an isomer of pentane, so C5H11 groups attached to the boron, provide some steric bulk. And so that prevents this boron from adding 2 times to both pi bonds of the alkyne. You follow this with peroxide, water, and NaOH. You get an enol, which, as you know from the problem sets, tautomerizes to the more stable carbonyl. Okay, so the carbon-oxygen double bond is especially strong. That is the driving force for that tautomerization. And tautomers are constitutional isomers that can be rearranged by the movement of a proton. Okay, to get a ketone out of this, we would treat it with acid and water. Alkynes are less reactive than alkenes, so they need a little bit more you need to add a mercury salt. Mercury sulfate is commonly used as a catalyst to get this going. So these reactions, well, especially the mercury sulfate acid and water, goes by a slightly different mechanism. So you do not get a carbocation here. The vinyl carbocations are especially high in energy. So we won't be covering mechanisms of these alkyne reactions, but this required you to read your chart, and I think that's a reasonable request. We will use these reactions in synthesis in a couple weeks. What part B? Provide 2 ways you would be able to distinguish between the 2 isomers with NMR spectroscopy. All right, so we've got aromatic ring with my aldehyde, and we've got my aromatic ring with my ketone. All right, so we would expect there to be a signal for this methyl group, a 3H singlet, and then we'd have a signal for the aromatic ring that's 5H and is a multiplet. We wouldn't be able to really distinguish that necessarily. We'd expect a 5H signal from the ring here as well, and here we would expect a 2H signal that is a doublet because we have one neighbor here. And for this one, we would expect a 1H signal that is a triplet because there are 2H neighbors on that side. And this will be shifted in the range of 9 to 10. The 2H doublet will be between probably 3 to 4 because we're going to have the withdrawing effect from the carbonyl and the aromatic ring, so it'll be further than you would expect. And then the 3H singlet here would probably be between 2 and 3 ppm. Of course, the aromatic region is going to be between 7 and 8 roughly, and so that's going to be the same. So 2 ways we could tell by the number of signals, 3 signals versus 2 signals, and then the splitting pattern. So it's not enough to simply say splitting pattern. You must describe that we would have singlet versus 1 doublet, 1 triplet. Okay. You could theoretically also speak to chemical shifts being different, but I think the more obvious signs is the number of signals, and then the splitting pattern will be very unique for both of these compounds. Okay. Ooh, my favorite next. Question 6. Determine the structure of the compound represented by the spectra provided on the back page. All right, so let's get to the back. All right, here we go. So kind of follow the same protocol for all of these types of problems. Start with IR, what bonds are present. Okay, we have this giant peak that kind of takes over here. This is going to be the OH stretch. You probably already can recognize that it'll be from a carboxylic acid. We have this matching CO bond. So we can go back and list those bonds. C double bond O and OH. The mass spec provides the mass, which is 194 or 96. It's not visible here. I tell you that it's a 1-to-1 ratio. So since there is an M plus and an M plus 2 peak, this is indicative of a halogen. The halogen in a 1-to-1 ratio must be bromine. Okay, so Br weighs 79 or 81. Does not matter which of those isotopes you use, but you must use the appropriate mass. So bromine weighing 79 is responsible for the molecular ion at 194. Bromine weighing 81 is responsible for the molecular ion at 196. In the mass spec, we see individual molecules. Individual molecules have one or the other isotope. You cannot use the periodic table mass because that's an average atomic mass taking into account the abundance of the isotopes. So you must account for the mass using the appropriate isotope. Okay, review the notes on mass spec that are posted. It works through those examples. Okay, so what do we know from mass spec? The mass is 184. There is a halogen. Okay, so I'm going to scroll back up here. Regretting putting it the way I did. 194. We have bromine. And then what functional groups could we be? We have a carboxylic acid. Looks weird, acid. And then we have a bromine. We don't have a nitrogen as well. We know that from the mass being even. Okay, so that's what we know so far. We have 194. We're going to subtract 79 and get a mass here. I'm going to cheat and use a calculator because I can. You are not able to use a calculator on the exam, but the math is not terribly difficult. I would do it in my head, except for I think it'll take longer. So anyway, and then we're going to subtract 2 oxygens. That's 32. That's 2O. I'm going to rewrite that as oxygen. And that gets me 83, and that's carbon plus hydrogen, right? And so we can start playing around with the numbers. I know that 6 times 12 is 72. So minus 72, that would be 6 carbons. And that gives me 11 hydrogens. Does that fit? So C, 6H11O2 Br. Well, it's not more hydrogens than you would expect. So if you went down to 5 carbons, you'd have 60 equals 23. This isn't possible. Okay, so this has to be it. What's the SOAP bar? 2 times the number of carbons plus 2 minus hydrogens minus halogens. Oxygen doesn't affect it, so we have 1 unit of unsaturation. 12 plus 2 is 14 minus 13. Hold on a second. Yeah, 12 plus 2 is 14 minus 12 is divided by 2 is 1. Yeah, okay. So we have 1 unit of unsaturation that accounts for the carbonyl. So we don't have any more rings or any more double bonds at all. All right, so then how do we put this together? Okay. Well, the spectrum is provided very nicely. So we have the COOH peak down here between 9 and 10. I'm not going to transfer this to the table. I'm just going to kind of write it on top of the spectra here. So we have a CH here. This is a triplet, so it has 2 neighbors. They could be on the same carbon or they could be on different carbons, right? Theoretically. If they were on different carbons, then we would have multiple 1H signals, and we don't have that, so they have to be on the same thing. So we have a CH2 here. We have 4 hydrogens, so this is some coincidental overlap. CH2 overlapping with CH2. We can't really tell what the splitting is for any of these, so that's okay. This 3H hydrogen is CH3. It's a triplet, and I see the expansion here. That's how I know that's a triplet. So it has 2 neighbors. And I suppose we need to pay attention to the chemical shift for this signal being way far down fields. This is probably attached to my bromine. Since there's only 1 hydrogen here, yeah, so basically we have our pieces now, right? So we have this group, we have this group, this group, this group, and this group. So we have to have 6 carbons, and I have 1, 2, 3, 4, 5, 6, 7, 8. I've accounted for 8 carbons, but remember some of them are duplicated here. So we're going to have 6 carbons in a row. 1, 2, 3, 4, 5, 6. One of them is a carboxylic acid. We have CH2, CH2, CH2. This could be my CH and the CH3 out here. So the fact that we only have 1 CH group means that the bromine has to be attached to that carbon, and the chemical shift tells me that it's shifted downfield due to the presence of 2 withdrawing groups. So it's beyond 4. If we're only next to bromine, and we'd expect between 3 and 4. If it was only next to the carbonyl, we'd expect 2 to 3. We don't really have either of those scenarios. So this is the only way it can be. So maybe a little bit tougher. The one on the exam is easier. So 1, 2, 3, 4, 5, 6, BR. Okay, that was fun. Part 2, reactivity and mechanisms. Circle the alkene that will react faster with acid and water. So this is related to the activation energy. We could form 2 possible carbocations here, and those are both secondary, and then this one would form secondary. So the fastest one will go through the lowest energy transition state. So we have my reactants and then my carbocation intermediate. So the lowest transition state will be the most stable carbocation. And that is for A. Okay. B and C we wouldn't be able to tease out because, at least with carbocation stability, moving into the next unit, we know that this is more stable than this. So the reactant energies will be what decides the activation energy. But that's not something you need to pay attention to right now. So moving on. All right, partial mechanism outlined below. Okay, what do I need to do here? In each box, draw the products of the mechanistic step, add curved arrows to show the flow of electrons, and label each reactant as a nucleophile or electrophile as appropriate. All right, so we have an alkene reacting with Br2 and methanol. Well, we know that the methanol is not a very strong acid, and we've seen alkenes react with bromine before, so we'll draw the expected product here, bromonium ion intermediate, and we make Br minus here. So then where are we going? For step B here, it looks like the methanol has added to the more substituted sites. So I have a clue as to what needs to happen here. This has to come in and break the Br bond. Now, not quite, I'm not going to be this picky, but based on the stereochemistry of the product, my bromonium ion would have had to form on the bottom side, right, as indicated here. Again, I won't be picky, but to be consistent with what is expressed here on the paper, this would be the outcome, okay? I have forgotten to label my nucleophile and electrophile. Nucleophile, electrophile here. Why does it attack the more substituted site? Well, you can imagine that we could draw extremes for this bromonium ion where that charge is shared over 2 carbon atoms. This is the major contributor since it is the most substituted carbocation and therefore the most stable. So when you think about the true structure being a hybrid, we can have this be a longer bond. There'll be a larger delta plus here than here and here. So the nucleophile will be attracted to the larger positive charge, not surprisingly, okay? So if things aren't making sense, we really need to talk because you got to be able to see the forest through the trees, right? See the big picture here and not get caught up in the weeds, okay? So the last step, we have a nucleophile and an electrophile reacting to give a neutral product, and that is this. Okay, so we have followed all the instructions. Make sure you get every piece that is asked for here, okay? Oh, label the mechanistic steps occurring in A through C above. So step A, was nucleophilic attack and loss of leaving group. Okay, so we attacked my bromine, and then we lost a Br minus, so that's the leaving group. Part B was nucleophilic attack and loss of leaving group again. Notice that the leaving group didn't fall completely off, it just left that electrophilic site, right? So the loss of the leaving group is happening here, and the attack of the nucleophile here. And part C is a proton transfer. I suppose I forgot to write the other product of this there, but you see the proton changes place, and that is a very classic example of that, okay? Okay, next is draw reaction coordinate diagram. All right, so we know reactants products, this is an electrophilic addition, so it's a energetically favorable process. We have one intermediate here. I'm going to label it I1 in purple. And then we have another intermediate here, I2. And the bromonium ion will be higher in energy than the oxonium because of the three-membered ring. And that's it. We have transition states here at each peak of that, okay? And we could draw the transition states if we wanted to. It's not asked for here, but bond making and bond breaking happening at the same time. So we're breaking a pi bond, we're making a bond between bromine on both sides, and we're breaking this Br bond. So this is getting delta minus, and then these, I would say, are getting delta plus, since they're giving up electrons here, okay? And of course, you could draw other transition states for the other ones. They're a little bit easier. Question 9. When 1,3-butadiene is treated with HBr, two isomeric products formed. Account for the formation of each. All right, jumping right in. We have a proton transfer to give the more stable carbocation. Of course, we could have direct attack of that cation to give me product A, let's call it. Or we could draw a resonance contributor of this structure, and Br minus could add there to give me product B. That was easy. So keep in mind, resonance could lead to other products because you have multiple sites that are electrophilic in these intermediates, okay? So this is not a rearrangement. Atoms did not move here, right? This is resonance where we only moved electrons. Right, and then we're getting near the end here. Fill in the missing reactant, reagent, or major organic products. So we know that bromination with a nonpolar solvent results in adding two bromines across the double bond. There's no possibility of rearrangements. This is stereoselective, but because this is not producing two chiral centers, the selectivity is not visible. However, you will get that bromine adding from the front or the back. This is racemic. It is inactive. Mercury acetate, water, and THF, followed by sodium borohydride. We know that has to be an alkene, right? Get your sheet out. This is a Markovnikov addition. So the best choice is going to be that terminal alkene. I would not award credit for this alkene because it would not result in the major product. Okay, so this is a pair of diastereomers. This would be active. You know, remember this chiral center did not change, and then we form a mixed set of centers there in the reaction. Okay, so these conditions produce alcohol via Markovnikov addition. Okay, so part C, treating this alkene with HCl, we have the possibility of forming two carbocations, this one or this one. And of course, that will cause this stereocenter to be mixed here once the H adds to that. Because this one is resonance stabilized, we will prefer that. And so this is why the bromine and the chlorine will add to the same carbon. Of course, this will produce addition of that chlorine from the front and the back. So this is a pair of enantiomers. It's racemic, therefore it's inactive. All right, and then the last one is going to go through this carbocation intermediate. We see acid conditions, we see branching nearby, hydride shift. Actually, I would prefer to do a ring expansion here because it's a four-membered ring, and it doesn't matter which of the bonds you do, it's symmetrical. So we're going to get this initially, and at which point we could do a hydride shift again. Redraw this nicely. 1, 2, 3, 4, 5. And carbon 1 has a methyl group, carbon 2 has a methyl group, carbon 3 has a methyl group, carbon 4 has a methyl group, and now it has the positive charge, at which point methanol will intercept, and ultimately you would get OCH3 here. I'm not showing stereochemistry because it would be a mixed center. I don't know anything about these other chiral centers, so I'm not going to pretend to draw out all of the 16 possible isomers for this. Okay, so that wraps up the reaction section, and then naming. Hopefully this goes pretty quickly. Start with the parent name, heptene, 1, 2, 3, 4, 5, 6, 7. It's a 3-heptene. It has to be, we'll come back to the stereochemistry later, but 2-bromo, 5-methyl, 4-propyl, 1, 2, 3, and then 3-heptene. So we have to rank this to make sure that it's Z. So looking at my high priority groups, let's draw this in half. So this is high priority here, and then we have carbon and carbon. So what's attached? C, C, H, and C, H, H. So this is my group. This as drawn is Z. So let me fix it. Yeah. So now my high priority groups are on the same side. Okay. The longest continuous chain, of course, is still 7. All right. I think that's easy to go from the name to the structure. And then we have to collect ourselves down here, find the longest continuous chain. Okay, so it's a decane. It's a derivative of decane. It would be a dec 2-ine. And then we have a 5-chloro, 8-chloro, 8-chloro, 9-methyl. So putting that all together alphabetically, 5, 8, 8, trichloro, 9-methyl, dec 2-ine. There is chirality indicated at carbon 5, so we have to rank these 1, 2, 3. This is clockwise. It is an R center. We only need to list the letter. We don't need to give a number here because there is only one chiral center, so it must be the only one that is R, okay? Yeah, so that is the exam. So after watching this, if you have questions, please let me know, and best wishes in getting prepared.